3-1s. Apologies again for being away, but we have some solutions for the Chapter 9 and 10 chapter test. And I'll just walk through how to approach some of these questions and hopefully get some clear answers. For number 1, it's asking for the x-intercept being 0.5, and then what is the value of k? So, the fact about here that isn't maybe as obvious is that if the x value is 0.5, the y value for an x-intercept is 0. So you can say that 0 comes out when a 0.5 is plugged in. So 0.5 plus a 1, and then subtract a 2, and what we can do is solve for k. Add the 2 over to this side, and a little cross multiply. That 1.5 slides up here. 2 times 3.5 is a 3.0, or a 3 for the value of k. Determine the asymptotes for this rational function quite quickly without having to break this up into a 6x minus a 12 plus a 12 minus a 9. Break this into its 2 fractions. Instead of doing this, which is way too much work, we could simply say, you know what, instead of saying that this is stretched by 3, 2 to the right, 6 up, we could simply look at the restriction on x and say the vertical asymptote is x equals 2. Your horizontal asymptote is based on this being a linear over a linear rational function, and because this is x to the 1, x to the 1, we look at the coefficients, and the horizontal asymptote is 6 over 1. So all of this was por nada, for nothing, horizontal asymptote 6. Number 3, which function has a point of discontinuity at x equals 1? What we're looking for is an x minus 1 factor on the top and an x minus 1 factor on the bottom, creating our point of discontinuity at x equals 1. Factor, we have an x minus 1 on the top, an x minus a 1, and an x plus a 1, point of discontinuity in letter A. Letter B, similar though, we have an x minus 1 and an x plus 1 on the bottom, but the x plus 1 factor doesn't relate to a point of discontinuity at 1, but at x equals negative 1 is the point of discontinuity, so no good. The top factors nicely, x minus 1, x plus 1, and the bottom has the x plus 1 factor, which again gives the same x equals negative 1 point of discontinuity, not what we want, and the top doesn't even factor, so that is kind of moot. Number 4, asking to sketch the graph of x plus 2 over x plus 2, x minus 2. Now again, these factors can cancel, which leaves us with a 1 over x minus 2 shape, as long as we continue with this x equals negative 2 point of discontinuity. So what we can do is we can sketch a rational function in standard form. This is like 1 over x, but it's shifting 2 to the right. There's no vertical shift after this, so we can say the asymptote is the x-axis, and then we can draw the shape 1 over x because there's no vertical shift. 1 over, 1 up. 2 over, a half up. A half over, 1 divided by a half is a 2. 1 divided by a quarter is a 4. And there's enough information to sketch. 1 over, 1 down. 2 over a half. A third, a quarter, and so on. Plug in a half, out comes a 2. Plug in a quarter, out comes a 4. And again, enough shape to draw this shape. Although I do have to be very, very careful because I did say there should be a point of discontinuity at x equals negative 2, so there should be a whiteout right there and a point of discontinuity at x equals negative 2. Identify the domain, range, and asymptotes. So there's going to be some good thought that goes into this one. The domain for this is that x is such that x cannot be a negative 2 and the vertical asymptote 2. But it can be every decimal and fraction in between. X is an element of the reals. For the range, we can say that y is such that y cannot be the 0. But there's also this hole punch, this point of discontinuity that exists at negative 2. And if I plug a negative 2 into the shape of this, 1 divided by negative 2 minus 2 makes a negative 1 quarter. That negative 1 quarter y value is your point of discontinuity. But it could be every decimal and fraction in between. There's your front page. As you flip it over, sketch the graph of 2 over x minus 1 minus 1. So similarly, we can draw in a vertical shift a vertical asymptote going 1 to the right, shifting 1 down, and then this vertical stretch by a factor of 2, being very, very careful. 1 over should be a 1 up, but we're going to stretch up to a 2. 2 over should be a half up, but we're going to stretch times 2. 3 over should be a third up, but we'll stretch times 2/3. A half over should be 2 up, but we're going to stretch to a 4, and that's as much as we can fit on here. 1 over should be 1 down, but it's to 2. 2 a half. 2 over a half should be stretched to 1 down. 1, 2, 3 over should be a third, but it's stretched to 2/3. And 1, 2, 3, 4 over should be at a quarter, but it stretches to a half. And there's as much, I think, as we can draw. Just to check, a half over should be 2, but we can actually make it to a 4. There we go. And this is a vertical stretch by a factor of 2. So you're drawing the 1 over x shape, but stretched vertically times 2. State the values of the x-intercept and the y-intercept. X-intercept looks like it's crossing at an x equals 3. Where does it cross vertically? At a y equals -3. This could be determined by plugging in for x equals 0. You could say that y is 0. And what you would find when y is 0, that you can sort of rearrange and solve for x. For number 6, solving algebraically, we can factor to determine the perfect lowest common denominator, which in this case it looks like there's an x minus 4 and an x plus 4, so we have to introduce that on every top. X minus 4, x plus 4, x minus 4, x plus 4, x minus 4, x plus 4. So everything in the denominator should cancel with this choice. X minus 4, x plus 4, it's all gone, we're left with an 8. The 1 has nothing that cancels, and I'll piece that back together. On the far right, the x minus 4's cancel, and we're left with a 1 times an x plus 4. Kind of nice. The x squared minus an x, there's a -8 minus a 4, -8 minus a 4 makes a -12 that equals 0. An x minus 4 and an x plus a 3 equals 0, giving us an x equals 4 and a -3, being very careful that one of the restrictions is a 4, so that one is an extraneous root. -3 is your only solution. For letter B, your lowest common denominator needs a 6, and it needs an x squared. You introduce your 6x squared on every top, and this should cancel out all of your denominators. The 3 and the 6, the 2 and the 6 makes a 3. I should cancel these a little bit more clearly. The 6x squared and the 2x leaves us with a 3x. Okay. Going back, the 6x squared and the 3 leaves us with a 2x squared. And the far right, it all cancels, leaving us with a 2 and the 13. Now I do want to be very, very careful because there were some things up there originally. So the 6x squared and the 3 is a 2x squared. That's with the 1. The 6 and the 2 makes a 3. And the x's cancelled, leave this x. But there was this 3 that was here, and I don't want to forget about that 3. And then the 2 is left over with that 13. Good. So we have a 2x squared, a 9x, and a 26. Moving it all over to one side, we have a 2x squared plus a 9x minus a 26. Hopefully this factors, otherwise we are in trouble. Let's just see, a 2x and a 1x, 13 and a 2. There's a 4 and a 13. Nice. One of these can be negative. So a -4x, 13x, subtracts to make a 9x. Good. This factors nicely as a 2x plus a 13 and an x minus a 2, giving us two solutions, a -13 over 2 and a 2. Neither of those are restrictions. It is good to double check these in your calculator. Even though this said algebraically, if you have time, type it in as y1, y2, where do they meet, and you will get your solution. We also talked about restrictions, and domain of some function m has f divided by a g. Now we do know that we can't divide by 0, and that you have to have a positive or 0 under a radical. So I notice on the top that if I try to draw out this on a number line, I know that 1/3 filled in, when is this inside equal to 0 is the cutoff. So when is this top greater than or equal to 0, I can solve for x and say x has to be greater than or equal to 1/3. So I feel like, all right, this is the case for the top. The bottom says that x minus 3 has to be greater than, not or equal to 0, just greater than 0. Because if the bottom were a 3 minus a 3, the bottom would be a 0, and that's a problem as a division. So here we're saying x has to be greater than 3. Open circle at 3. So these x values have to work with everything. So imagine I were to say, let's plug in a number like 1. It'll work on the top, but it won't work on the bottom. So where both of these colors overlap is our overall guiding domain. X has to be greater than or equal to 3, every decimal and fraction in between. Here is your domain. So it's kind of like, pick a number like 4, it'll work here, it'll work here. Plug in a number that works in only one, and it really won't work with both. Number 8, from the graph on the right, determine the values of f minus g of 2. This is like saying, what is f of 2 minus g of 2? F of 2 minus g of 2. What is f of 2? Here's f, plug in a 2, 3 comes out. G of 2, here is g, plug in a 2, and a negative 1 comes out. 3 minus negative 1 is a 4. F plus g of 2. What is f of negative 2 plus g of negative 2? Find negative 2. F of negative 2 is a negative 1. G of negative 2 is a negative 3. And a negative 1 plus a negative 3 is a negative 4. What is f of 1 plus f of 1? Go and plug in a 1. Out comes a 2. And another 2. Out comes a 4. Lots of 4s. For number 9, determine an equation for h of x, which looks like if f is your overall structure, and it looks like g is getting plugged into it. So a sine of x is getting plugged in. So this is your function h of x, and maybe we can tidy this up a little bit by saying h of x is a sine squared plus a 5 sine x. Now this should look very familiar, and it's possible to incorporate some trig and some logs and some rationals and radicals in one unit. So here's your equation h of x based on x. For letter b, what is h of pi over 2? So if you plug in a pi over 2 into this equation, what do we get? What is sine of pi over 2? Oh my goodness. Plus 5 sine of pi over 2. Now we think about the unit circle for a moment. Yes, we think about the unit circle. Pi over 2 is 90 degrees. What is the y value up at the top? The y value at 90 degrees is 1. This is a 1 squared plus a 5 times a 1, and we have a 1 plus a 5 is, final answer, 6. Number 10, use the following table to evaluate. F of g of 1. Here's an input of 1 going into the function g. Input of 1 going into the function g, 6 comes out. Now we have f of 6. This is a composition. F of 6. 6 is your input into the function f, 5 comes out. G of f of 3. What is f of 3? F of 3, plug in a 3 into f and a 4 comes out. What is g of 4? 4 goes into the function g, 1 comes out. F of 5 divided by g of 5. F of 5, plug a 5 into f, 2 comes out. Plug a 5 into g, 2 comes out. 2 divided by 2 is 1. G of 1. So plug a 1 into the function g, and a 6 comes out. Plug a 6 into the function g, 3 comes out. Final answers. Number 11, find two functions f and g such that there is some overall structure in f, which looks like something got plugged into this repeatedly. So I might say that this is an x squared plus a 5x plus a 7. That's the overall structure f of x. And what got plugged into this g, what got plugged in as g, is this repeated 2x minus 1. This is one possible solution, but this is the most likely one that students would tend to answer. On to the back page, number 12. A function has been transformed from this 1 over x base shape, 4 up, 3 left. So this is an x value of -3, x minus -3, up 4, after being vertically stretched by a factor of 2. There we go. Determine its equation in maybe simplified form as one fraction. Now, to make this possible and not see two fractions, we would need a common denominator, x plus 3. Now, x plus 3, we can tidy this up and say 2 plus a 4x plus 3 over our common denominator, x plus 3. What we end up with is a 2 plus a 4x plus a 12 over an x plus 3. And a final answer, 4x plus a 14 over an x plus 3. Final answer, A, B, C, D. Number 13 is our last question on the quiz, on the test. And it asks, for the following graph, determine an equation in a single fraction form, kind of like above where we combine things into a single fraction. The numerator and the denominator should also be simplified. So what we have is, it looks like a rational function, this 1 over x shape, and it looks like there's a vertical asymptote. It also looks like there's a horizontal asymptote. And important to note, there's a point of discontinuity at x equals 2. So let's start with this shape, a over x minus h plus k, and identify what we know. I can see that this is shifting 4 to the left and vertically 2 up. Now, what we don't know is this a value, but I can clearly see that there is some points identified. What can we tell? Here's a point that it looks very clear. 3 to the left, 5 up. 3 to the left, 5 up. That's one example that I could find. There's probably a few other ones like this one. I could find this one. Lots of possible choices. But let's plug in a -3 and say that a 5 comes out. -3 plus 4 plus 2. We can subtract the 2 over to make it a 3. That equals an a divided by a 1. And in fact, an a is a 3. That kind of makes sense because from our new origin, 1 over should be 1 up, but it's actually 1, 2, 3 up. Vertical stretch by a factor of 3. So our equation now becomes y equals 3 over x plus 4 plus 2. We haven't considered this point of discontinuity yet, but we also have a bigger issue right now that this is not really a single fraction. So we can do the same thing as we did initially a moment ago and create a common denominator, bring this together as a 2x plus an 8 plus a 3 over our common denominator. And this is what this shape looks like without our point of discontinuity. So now that we have a common denominator, let's introduce this point of discontinuity as our x minus 2 over an x minus 2. Now we've got the point of discontinuity introduced back in, and for a final answer we need to determine a single equation in a single fraction form. Numerator and denominator should be simplified. There will be a 2x squared. There will be a -4x plus an 11x minus a 22. An x squared minus a 2x plus a 4x minus an 8x. And there will be your final answer. What's the domain and the range for the function above? Very, very similarly, we can talk about this domain as x is such that x cannot be a -4. It also can't be that hole punch 2. That's an issue. And for our range, we've got our y value that cannot be 2. Ooh, but it also can't be the y value at the point of discontinuity. We have to look at our equation, maybe before we introduce x equals 2, and plug it in to see what we end up with. So if we say y equals 2 times 2 plus 11, so I'm picking the equation that this follows, divided by a x plus 4, and we end up with a 4 plus 11 divided by a 6. this maybe could be tidied up a little bit. Divide by 3. 2.5 is our other restriction, and y could be anything else. That is your Chapter 9 test. Good luck.